In this video, we're going to introduce colligative properties, and the four colligative properties specifically that we're going to talk about are noted here. So first we have vapor pressure lowering, then we have freezing point depression, third is boiling point elevation, and the fourth colligative property is osmotic pressure. So we should note that these colligative properties and others depend only on the number of solute particles present, not what type of solute we have. So just the number. So we'll look at how we figure that out and how that affects these colligative properties, specifically using molality for some of these calculations. So first, let's look at vapor pressure lowering. So vapor pressure is defined as the pressure exerted by the vapor when it's in equilibrium with the liquid. So whatever volatile substance, whatever is producing this vapor pressure is in equilibrium, this dynamic equilibrium between condensation and vaporization. So we have this liquid gas dynamic equilibrium, similar to the dissolved crystallization equilibrium that we saw with our discussion on solubility. If we refer to something as being non-volatile, that means that it has no measurable vapor pressure. So it's a solid or liquid that does not become a gas very readily, versus something that's volatile does become a gas fairly readily. So we have volatile solvents and then we have non-volatile solvents. And this has to do with the interaction between molecules. So what we see here is that if we have a non-volatile solvent or solute rather added to our solution, it's harder for the solvent to vaporize. So we can actually see a lowering of vapor pressure when we add these non-volatile solutes. So we can continue this discussion here and say that the vapor pressure of a solution, then we can always assume to be less than the vapor pressure of our pure solvent. So a solution would have that added solute, whereas this is just the solvent. So higher vapor pressure for the solvent than the solution. And we can use this relationship here defined as Raoult's law, where our pressure here of our solution, so this is of our solution, is going to be equal to the mole fraction of our solvent. So this would be the larger fraction. So the solvent is always present in a greater quantity. And then we multiply that mole fraction of the solvent by the vapor pressure of our pure solvent. So these variables are defined here. And we can also note this definition of an ideal solution. When we refer to an ideal solution, it will be one that obeys Raoult's law. So let's take a look at an example in sample exercise 7 here. And we're told that the vapor pressure of pure water, so this is our pure solvent, we're given a temperature, but we don't need that for our calculation. We just need our vapor pressure for our pure solvent, and that's 1070 torr. Then we have a solution of ethylene glycol and water. So this is commonly used as an antifreeze solution with a vapor pressure of 1 atmosphere. So that's the vapor pressure of our solution. Notice they're in different units. We'll have to attend to that before we can do our final calculations. And we're assuming that this solution is obeying Raoult's law. So we want to know what the mole fraction of water is. So we're solving for the mole fraction of our solvent. So from our equation above, we can say that the pressure of our solution is going to be equal to the mole fraction of our solvent times our partial pressure of our pure solvent. So we have all this information. Let's just arrange it here. So first I can most easily convert atmospheres to torr. So I'm going to take this 1.0 atmosphere and convert that to torr. If you remember, it's the same conversion factor for torr as it is for millimeters of mercury. So I'm going to have 760 torr for my pressure of my solvent, my pure, I'm sorry, of my solution. So I'm going to put that over here. So I have 760 torr is going to be equal to the mole fraction of my solvent, and then that's going to be times the 1070 torr. So if I rearrange this equation, divide both sides by 1070, I can then see that my mole fraction for my solvent, my water, my H2O, is going to be just 760 divided by 1070, or that is going to be about 0.71.